All right, give me a... Okay, welcome again. Tonight, the plan is to spend an hour and a quarter or so talking about logarithms and exponentials. That's chapter 9 in my book. That's the last topic before the Math 103 midterm. And hopefully I can get it done in an hour and a quarter, which will leave me 45 minutes of the regular time to do a review of the review, as it were. Everything that we've done so far in 45 minutes. Well, obviously, I'm not going to be able to give too many examples, but what I'll do is provide a map that will help you in your studies before tomorrow evening. So that's the plan. After 9:30, the video will cut out, but we'll do question and answers. Hopefully you've brought some questions, and hopefully I have some answers. So before I begin, any quick questions about the plan? Okay, well, logarithms and exponentials. Let me start off by saying a little bit about logs. So this is working in actually section 9.1.2 of my book. I want to just start off with a very brief review of logs, just for a few minutes. I want to remind you that if you want to solve this equation, 2 to the what equals 7, by definition, the solution is x is log 7, and you need the base of 2 so that both of these numbers come in. So this actually is the power that you need to raise 2 to, or the exponent that you need to raise 2 to the power of in order to get 7. Okay, so that's the way I look at a log is I see the log. This to me is an exponent. It belongs up in the exponent. In fact, if you take these facts that if 2 to the x equals 7, then x is log 7 base 2, and you surgically insert this log 7 base 2 instead of x, you are forced to conclude that 2 to the power of log 7 base 2 is 7. That's a weird-looking equation, but that is the definition of log 7 base 2. In general, if b is any base, positive number, it's true that b to the log y is y, provided that the log is to the same base b. So that's a useful equation to know. And it is one that is sadly neglected. Somehow, even though that's the definition of log y base b, somehow this equation seems mysterious. So try to wrap your minds around that. Now, what do I even mean? Well, the best way of looking as to why this should be true is to consider the graphs and consider inverse functions. Next time, which for the people in this room will actually be in 2 weeks' time because of the break, we will look at inverses in great detail. But for the moment, I just want to consider the graph of y equals b to the x. In fact, let's call that f of x. Let's set f of x equals b to the x, where I've picked some base b, and let's say it's greater than 1. If it's less than 1, then the curve would actually look like this, and it gets a little bit messy. So I'll just assume that the base is bigger than 1. There is an inverse function because this satisfies the horizontal line test. And the inverse function's graph has got to look something like this. So this is the inverse function, and it turns out that that is what we're calling log x base b. After all, this undoes the exponential. So that equation justifies this as being the inverse. So here I have g of x is log x base b. And if there's any justice in the world, if f and g are inverses, which I've said they are, then we should have f of g of x should be equal to x, because f should undo the action of g. So what does this mean? This means b to the power g of x, which is b to the log x base b. And as we see from this equation above, if you just simply change the y to an x, you get x. So yes, f of g of x is x as long as x is greater than 0. Why does x have to be greater than 0? Well, you can see it from the graph. The domain of log is only x greater than 0. There's nothing over here. And I'll write that down in a few seconds. But before I do, I want to just look at what g of f of x is. That is the log of f of x, because after all, g is the same as log base b. So of course this is log of b to the x. And this also should equal x. As we will see with the log rules in a few seconds, that's true. So f undoes g and g undoes f. You start with x. If you do g first, you are taking the log, then you raise it to the power of b, or b to the power of it rather, you get x back. Same if you take the b to the x first, then take the log, you undo it. So from this graph, we can sort of deduce some elementary properties of log. In particular, the domain of log is 0, infinity. It's just positive numbers, right? The range is all of r. And we can already notice a few limits from the graph that I want to come down to, I want to come back to shortly, but the limit as it goes to infinity is still infinity, doesn't have a horizontal asymptote, it keeps on going up and up. But as you go to 0, there's a vertical asymptote here. It's just taken the horizontal asymptote of b to the x and turned it into a vertical asymptote. And so as you approach 0 from the right, you can't approach it from the left, of course, because log isn't even defined, but as you approach it from the right, you go down to minus infinity. So those are some pretty basic facts about log. Now, there are also log rules that you're expected to know. And these follow directly from the exponential rules. There are actually proofs of them in section 9.1.4. I'm certainly not going to do it tonight, but I do want to state what the rules are. So here they are. The log of 1 to any base is 0. That is because b to the 0 equals 1. That's another way of looking at this. On the other hand, log b to the same base is 1, because b to the 1 equals b. The others are a little more complicated. The log of a product actually is the sum of the logs. Without proving it, let me just say that if you interpret log as the exponent, remember when you multiply two exponentials with the same base, you actually add the exponents. That's exactly what's going on here. This is an exponent, and these are both exponents. Of course, the same is true if you divide, except that you've got to subtract log. And there's this nice other property that log of x to the y, the exponent inside the log, comes down out the front of the log. And that's equivalent to the fact that if you have a or b to the x all to the power y, that's the same as b to the xy. The extra power there comes out the front and just multiplies. So those are the main log rules. There's also a sort of other log rule that's a little bit different from them that doesn't come up very often, but it's useful occasionally. Change of base rule. Let's see, state this the same way I did in the book. The log of x base b, turns out that's the same as the log of x base c, but you have to divide by a correction factor, which is the log of b base c. Now, you've probably seen all these before. I just have one thing to say about the change of base rule. If you think of this as a function of x, but you fix b and c, so b and c are just some numbers, like 2 and 3 or something like that, but you consider this as a function of x, then all this says is that this function is the same as this function times the constant 1 over log b base c. See, this bottom is just a constant because it doesn't depend on x. If you fixed b and c, then it's just a constant. So that means that changing the base doesn't really change this graph much. All it does is stretch it out or shrink it. So all the different logs, are the same function. They're just stretched out by some number. That's all the base really matters. So actually, the base doesn't matter very much. That change of base rule tells us that. All right, so that's all I want to say about logs until we do some calculus with them. Are there any questions about this basic stuff? All right. Let's talk a little bit about compound interest. So this is seemingly unrelated, but hopefully everything will tie together. Suppose you have some amount of money in a bank account, and let's give it a 12% interest rate per year. That's pretty generous. If you look after 1 year, you started off with a certain amount of money, say A. After 1 year, you will have 1 plus 0.12, that's 12%, times A. That's compounded, okay? I don't even want to look at what happens if you have multiple years. Instead, I want to ask, suppose that your bank actually compounds twice a year. So instead of once a year at 12%, at the end of the year they say, okay, we're just giving you 12% extra. They say, twice a year we're going to give you some money. But of course, they're not going to give you 12% both times. They're going to give you 6% because they do it twice a year. So this is compounded once per year. If you compound it twice per year, then each time you compound it, you increase your fortune by a factor of 1 plus 0.06, but you do it twice. So rather than think of it as 0.06, I want to think of it as 1 plus still the original rate, but divided by 2. So which one is greater? This or this? This has the higher rate. This is only 6%, but this is done twice, and this is done once. Well, it turns out it's better to compound it twice. You can plug it into a calculator, work out these numbers, times A is the same in both cases, and you find that the second one is bigger. And actually, if you look in section 9.2 of the book, you can find out what those numbers actually are. I just calculated them. Anyway, so you might say, well, why stop there? Why not do it 3 or 4 times? You know, you could do it n times. Of course, if you do it n times a year, you need to divide the rate by n, because you're not going to compound at 12% every time. You're going to compound n times, each one of them at 12% divided by n. But every time you compound, you multiply by a factor of 1 plus 0.12 over n. So you need to raise this to the nth power. So this is the effect of compounding n times a year at 12% for 1 year. Let's just try to generalize this formula. The 12 doesn't have to be 12. It could be r, where r is any number. And instead of doing it for 1 year, I could maybe do it for more than 1 year, in which case I just have to raise this power to the number of years. So if I do this for 2 years, I'm going to have a 2n there, because it's really this squared. So basically the general formula looks like this. The amount that you have so without the t, that's the same as this formula with r replaced by 0.12. The t allows you to do multiple years. So this is the amount. You start with A. You compound n times a year at a rate of r for t years. And there's no calculus in that. That's just pre-calc stuff. But you do need, clearly, some exponentials in there in some sense. I mean, you're raising something to the power of something. Okay, so that's a formula that you're probably expected to know, even though it comes straight from high school. Now, this dude called Bernoulli, and I don't remember which one they were. There were quite a number of Bernoullis. That one of them had an effect. Maybe this is the same guy. Never mind, this isn't a history lesson. A dude called Bernoulli a long time ago said, well, it's better to compound twice than once, And it turns out you can easily calculate it's better to compound 3 times than 2 times. In fact, the more times you compound, the better. So is there any limit, as it were? Is there any sort of top to the thing? Forget the word limit in calculus sense. What I mean is, if you compound like 100 billion times a year at the rate of 12% over 100 billion each time, but you're just doing it all the time, compound, okay? Do you not make scads of money? Don't you become a billionaire in 1 year? And the answer is no. There is a speed limit for increase of fortune just by repeated compounding at the same annual rate. And without further ado, I will tell you what it is. It turns out that if you take 1 year of compounding, this is $1 at a rate of R, n times, so it's the same as this formula, but you started off with $1 and you're only doing it for 1 year, so A is 1 and T is 1. And you let n go to infinity. That means you compound more and more times a year. It turns out that this converges not to infinity. It converges to a finite number, which is e to the r, where e is defined by this. So you start off with an interest rate of 100% a year, and you compound that more and more often. That will give you E times your original fortune for the year. And it turns out that E is a number like pi. It's an irrational number, and it's sort of naturally part of the universe, as it were, just like pi. It turns out that E is about 2.718, something like that. The decimal expansion goes on forever and never repeats itself because it's irrational. But you should think of it as around 2.7. That's actually all you really need to know about it from that sense. And so, of course, if r equals 1, that reduces to that formula. The beauty is that you get an exponential dependence, e to the r, on the interest rate. And so you need to know both of these formulas here. Of course, this is a specialization of this when r equals 1. So Bernoulli worked this out and said, you know what, there is a speed limit of increase of fortune, even if you compound 100% over and over and over again, dividing each time, of course, by the number of times. The most you can get is e. To put this in perspective, if you do 100% once a year, just once, then you double your money. So you've gone from A to 2A, so the factor is 2. If you take that same rate and do it more often, the best you can do is 2.7, a little bit over 2.7. Okay, so that's a nice little fact. So E pops out quite naturally from this whole sort of thing. So here's the deal. Take this formula here. What happens if you compound infinitely often? Well, I want you to take this formula and take n goes to infinity. As n goes to infinity, a1 plus r over n to the nt looks like this. This converges, as n goes to infinity, to a e to the r to the power t. See, the stuff in the brackets goes to e to the r. So that's why we get this. And of course that is equal to a e to the rt. So here's the deal. That formula there gets replaced by this. So this is start with a, but you compound continuously, infinitely many times a year. For t years at a rate of r. And you need to know this. So notice there's no n anymore. N is sort of infinity. That's the result of taking that formula in the box, the top box there, and replacing n by infinity. Of course, you can't actually replace n by infinity, but if you could, then it would look like this. Instead, you can take a limit as n goes to infinity, and that's what you get. So you're expected to know both those formulas there. In fact, all four of the formulas in boxes. Although I have to admit that right-hand box is a pretty weird box. Okay. So that's supposed to give some motivation of where E comes from. By the way, there are two other limits that you're expected to know. In this limit up here, if we can just focus on there for a second, see, n gets very large. So if you replace n by 1 over h, then h gets very small. So I can rewrite this limit in an alternate form, limit 1 plus rh to the power 1 over h, as h goes to 0, that is also e to the r. And that's a useful limit to know. Right, all I did was I substituted h equals 1 over n in the previous formula. And of course, this specializes to this useful limit. Limit of 1 plus h to the power 1 over h is e. By the way, when you look at a limit like this, it's a mistake to plug in 0, say, oh, this goes to 1, therefore 1 to the power of anything is 1, therefore the limit is 1. That's a mistake. You see, although this is 1 plus a little bit, and it is going to 1, you're raising it to a huge power. And if you raise it to a huge power, then somehow everything balances out and you magically get this e. Doesn't make... It's a little surprising. It makes sense in a way, but I think it's a little surprising. Okay, great. So there's a little bit of calculus because we've done a limit. As I'm erasing the board, if anyone has a question, just start shouting it out. No questions, so I'll keep on going. Right, because we have this new base e, or this new number e, which is an exponential, we've been dealing with e to the power of so-and-so, it makes sense to deal with logarithms to base e, and we'll soon see why that's a really nice base to use. So instead of log base e of x, I'm going to write ln of x. So the n stands for natural. This is the natural logarithm. This is the same thing. Some people say ln x, but I have a friend called Lynn, and she's not a logarithm, so I instead just say log. Or you can say natural log. Or if you really want to ln of x, that's fine. Just, try to be stylish and not say ln x. Okay. Anyway, just a little pet peeve. It doesn't really matter. You can say whatever you like in your spare time. I don't care, as long as I don't hear it. So in any case, we have this natural logarithm, and it obeys the same log rules that any other base does. And of course, you could just rewrite them for yourself, but I think that it's worth my rewriting them a little bit, or just really quickly. Here are the log rules base e, just using this new notation. Log of 1 is 0. Log of e is 1, right, because e is the base that we're taking it to, and log b is 1. Of course, the log of the product is the sum of the logs. We also have that the log of the quotient is the difference of the logs. The log of an x to the y, an exponential like that, the power still comes out. And finally, the change of base rule. How do I want to write that? Do I even want to write that? Maybe I do want to write this. If I have log of x base b, this is the same thing as the natural log of x over the natural log of b. That's the change of base rule, but instead of the number c that I had from before, I've replaced it by e. And if the base is e, you don't write log, you write ln. Actually, to tell you the truth, mathematicians write log x with no base, and they mean ln. They mean natural log. 10 is not a natural base to use. 10 just happens to be the number of fingers we have. Nature should have given us e fingers from some point of view, but that would be pretty inconvenient. I don't know what 0.7 of a finger would look like, for example. In any case, so base e is the natural base to use. Okay, so those are the log rules in there. Where this whole stuff really shines is when you try to differentiate. So I'd like to move on to section 9.3, which is where I'm going to show you how to differentiate log. Now this, you do not have to know, at least at Princeton, how to derive this. You need to know the result, but it's not so long to show this, so I want to show it to you because it's kind of nice. Suppose you let y, actually instead of y, I'll call it f of x. So this is the log function. I just had drawn the graph of it. It seems pretty smooth, so it should have a derivative. What is its derivative? We want to find f prime of x. Who knows? Well, here's what we do. We write down the definition of the derivative, possibly for the last time, at least in a while, or last time for a while. This is something you have to know for the midterm, of course. You need to know that formula at least. That's our old chestnut of a formula. And of course, in this case, f is just the log base b. So I'm going to replace f in both places by the log base b. Now, I'm going to start using my log rules. The first thing is this is a difference of logs, so I can write it as the log of the quotient. So the factor 1 over h, that's the denominator over there. I'm going to write this as the log of x plus h over x. So that's a log rule. Now, let's just simplify that. Let's write this as log 1 plus h over x. Okay, I just split up this into x over x plus h over x, and x over x is 1. Now I'm going to use another log rule. Actually, I'm going to use, let's just focus on this log rule. I have something times log x, so I'm going to write it as log x to that power something. Here it is. Log of blah, this has got to be equal to log of 1 plus h over x to the power 1 over h. See, this factor out the front jumped up and became the exponent. Now, take a look at this. Take a look at this. This is the same as this, except that r is replaced by 1 over x. Okay, stare at that one. This may be good camera work here is required. Somehow stare at that one. Mentally replace r by 1 over x. And you see that you get this one. In fact, I'll make it even easier by spelling it out. Wait, I still need the limit. One plus 1 over x times h to the power 1 over h. Okay, so the point is that this goes to e to the r in the limit. So I can finally take the limit, and it's e to the r, but r is 1 over x. And that is the result of taking the limit. And there's not very much left. All I have to do is use one more log rule. I pull the 1 over x down outside the log. There it is. 1 over x log e base b. fact, one more log rule to use. If you look at that change of base rule up there, the last one on that top column, instead of x, I'm just going to write e. So this is 1 over x natural log of e over natural log of b. But the natural log of e is 1 by yet another one of those rules. And so you end up with the 1 over x log b, natural log of b. So in conclusion, we have shown that the derivative of log x base b is 1 over x times the natural log of b. Okay, don't worry too much if you didn't follow all those steps, although it's a really good test of your understanding of the log rules, by the way, to make sure that you followed all of that. The key point was that when we took the limit, we used our previous limit from the compounding of e. That's where the e came from. Now, by the way, when b equals e, then of course this is just a natural logarithm, and we'll have log of e there. So it's 1 over x log of e, but of course log e is just 1. And you have, therefore, this formula as a specialization of the above one. The derivative of log x, natural log x, is just 1 over x. Amazing. It really is quite an extraordinary formula, that. It's the sort of thing that you would really never guess. It's an amazing formula, actually. But the derivative of log is just a power. It's x to the minus 1. Anyway, it's quite a crucial fact. In fact, the entire banking industry depends on that, in some sense. And I say banking industry, inflation depends on that. So in some sense, all of economics. And that's not the only thing. Population growth depends on that sort of thing. Radioactive decay depends on it. So it's very ubiquitous in the natural world, and it just took a long time for humanity to realize that fact. Ancient Greeks did not really know that, for example. Okay, we have another couple of derivatives to learn, and then we can start looking at some examples. I've done a lot of theory so far, presented some formulas. I mean, there's some trivial problems involving the formulas I've written so far about compound interest, but I'm not really interested in just applying formulas. I've got to develop a little more material. Look, suppose y equals b to the x. We might as well differentiate that. It's not that hard. You see, if y equals b to the x, then x is log of y base b. If that's, you have to be able to do that, by the way. If y is b to the x, solve for x. You have to be able to write that x is log y, and then the base must be b. Don't get these the wrong way around. There's no need to get them the wrong way around. Log y, base b. Here's the base, b. Y is not the base. Anyway, this we can differentiate with respect to y. dx dy, according to the formula that I just wrote up, is 1 over y natural log of b. That's for any base. Because I want to find dy dx, and I don't know how to do that yet. So I've got y as b to the x. See, I don't know the derivative of this. But if I make x the subject, if I solve for x, I can take dx dy, and then I can flip it using the chain rule and say that dy dx is y log of b. But what is y? Y is b to the x. So by these shenanigans, we've actually differentiated b to the x. And we have shown that d dx of y, b to the x, is b to the x log of b. And that is a formula you must know. d dx of the derivative of b to the x with respect to x is b to the x times the factor natural log of b. All right? So you need to know that. What if b itself is equal to e? Well, if b is the natural base e, then log of e is 1. Natural log of e is 1. And so actually this specializes to the derivative of e to the x is e to the x times 1. And there you have it. There is a function whose derivative is itself. How about that? Actually, we already knew a function whose derivative is itself. 0. Y equals 0. dy dx equals 0. That's not a very interesting function. This one is an interesting function. This is the only non-trivial function whose derivative is itself, except for a multiple of it. 3e to the x. The derivative is 3e to the x. Okay. But apart from multiples of this, that's the only function which is its own derivative. Pretty nice. Okay. We have 4 new derivative rules. Log x, base b, natural log of x, b to the x, and e to the x. We have product rule, chain rule, quotient rule, and we have all our other functions, sines, cosines, and x to the 3, and all that sort of stuff. You have to be able to add these formulas into the mix. So just as a sort of simple example, and this one comes from 9.3.1. Actually, I want to do 2 examples from this. Suppose we want to find the derivative of sine of 3x. Wait a second, that's not exponential. I talked about this sort of thing before. You could use the chain rule. In fact, you do use the chain rule. But because this is such a simple function of x, it's just a multiple, we learnt before that when you differentiate ax, a function with ax replacing x, you just multiply by a, that constant function. So the way I think of this is the derivative of sine x would have been cosine x. So of course, that's going to be true, but I need to multiply by the 3. Again, you can, if it makes you more comfortable, you can let u equal 3x and then use the chain rule in gory detail, but that's kind of a waste of time at this point. Why do I bring this up? Because the same thing goes for e to the x, say. If I differentiate e to the 3x, or minus 3x, I think is the example I have in the book. So I take e to the minus 3x and I want to differentiate it. Don't waste time with the chain rule. I've just replaced x by minus 3 times x. And so because the derivative of e to the x is e to the x, the derivative of e to the minus 3x is e to the minus 3x times minus 3. It's exactly the same template. So the derivative of e to the 7x is 7e to the 7x. Not so bad. Of course, if you do get something more complicated like this, what is the derivative of log base 3 of x squared plus cosine x? To find this, maybe it's better to use the chain rule. So I'll set up a little table of working. I'll let y be this function that I'm supposed to differentiate. And I'll let u be the inside bit, x squared plus cosine x, so that y is simply log u, base 3, of course. So we're going to need dy du by the formula that I wrote before. This is 1 over u, natural log of 3. We're also going to need du dx from up here, and that is very easy. That's just 2x minus sine x. Don't forget the derivative of cosine x is negative sine x. That's the most common mistake I've ever seen when grading calculus exams. The derivative of cosine x is sine x. Okay? Minus sine x. The derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Okay, so in any case, this, of course, is dy dx, because y is the nasty thing. And, of course, that's dy du dx. dy du is 1 over u log 3. Du dx is 2x minus sine x. Now I have to go back to x land. I'm in u here, but u is this expression x squared plus cosine x. Oops. So there's that, and I might as well consolidate and put the numerator here, 2x minus sine x. Okay, so that's the derivative. Again, all I did was use the chain rule, but with my new formulas. In this case, I only needed this new formula, actually this one over here, with b equals 3, and then the chain rule. Okay, but make sure you can do it. It's nothing new. It's really nothing new, but it looks a little different, and it's the sort of thing that you should practice. Question?
Do we need this for the test tomorrow, because in none of the old midterms they have to do such things?
This is a very good question. Do you need this on the midterm? And I actually don't know the answer for sure, but it is highly possible the answer is no, especially if you haven't seen it on old midterms. Okay? We will try to resolve this question at 9:30. Okay? I'm sorry, I haven't seen the midterm, so I don't, even if I had, I couldn't tell you what was on it, but I will try to clarify that for you. In any case, if you don't need it for the midterm, you'll certainly need it after the midterm, and it'll all depend on when you actually covered it in class. Wow, I'm actually ahead? Does this mean I'm ahead of something that you have to study for? Amazing. Anyway, so I'm making good time. Here's the deal. There's only two other things that I would like to show you about. One is a collection of limits that involve E, and this may be on the midterm. I think I've seen something like this, or it may potentially be on the midterm. And the other is log differentiation. And those are the two things I have to do. They should take me about half an hour, and then I'm going to start from the beginning and do this 45-minute potted summary of the course today. Okay? So, in section 9.4, I go over a whole bunch of different limits, 5 different types, and I don't propose to spend much time on any of them, but I do want to spend a little time on all of them. Suppose I ask you this limit, and I'm pretty sure I have seen this on previous midterms, this sort of question. Suppose I ask you the limit as h goes to 0 of 1 plus 3h squared to the power 1 over 3h squared. What should that limit be? Well, consider this limit. What should that limit be? Actually, I wrote that up before. It's been erased. Does anyone remember what that is? E. Okay, so what's that limit? It's actually also E. You see, the template that I want to use is this. What's the limit as x goes to 0 of sine x over x? 1. So what's the limit as x goes to 0 of sine 3x squared over 3x squared? That's also 1 because they match. It's sine small over sine small. Well, here's 1 plus h to the power 1 over h. As long as these are the same small quantity, and that small quantity is going to 0, then the limit will be e. So in this case, 3h squared goes to 0. As long as you replace it in both places, you'll get e. Right? You can think of it as doing a substitution. I replaced h, and h here by 3h squared. So maybe I should have written 3h squared goes to 0 up here, and then it really is this. Of course, h goes to 0 and 3h squared goes to 0 is the same thing. So it's correct as it stood. Okay, so that's a sort of tricky thing. After the midterm, we'll do L'Hopital's rule, actually quite a bit later. And that provides another sort of way of doing this, but you don't really need it. You can just take this standard limit and get this. I just want to show you one little variation. There's some others in this section of the book, but they get a little tricky. I'll just show you one simple variation. Suppose you have to do limit as h goes to 0 of 1 plus 3h squared to the power 1 over h squared, not 1 over 3h squared. Well, you have to do a similar sort of thing of multiplying and dividing, except you can't really do much down here. This is the best place to work. What I really wish this said, I wish this said 1 plus 3h squared to the power 1 over 3h squared. I wish it said that. Unfortunately, it does not. It is 3 times as much. See, I made this match this, but then I had to compensate by a 3. So I did multiply and divide by 3, actually, in the exponent. The nice thing about doing this is that you can write this as 1 plus 3h squared to the power 1 over 3h squared, all of this cubed. That's just by the exponential rules. Now, 1 plus small to the power 1 over same small, that goes to e. So this whole thing is e cubed in the limit. So if you have any questions about that, you might as well start shouting them out. Was that a question or just a moan or a stretch? You're allowed to moan since you have a midterm tomorrow. I will permit expressions of grumbling while I erase the board. It's permissible. All right, enough. No more grumbling till the next time. This doesn't count. Okay. So, again, there are some more examples in 9.4.1. But 9.4.2, I'd like to explore this. E to the 0 is 1, because anything to the power of 0 is 1, at least, provided not 0 to the 0, which doesn't even exist. Okay, so what's this? Limit as x goes to 1 of e to the x. I'm sorry, limit as x goes to 0 of e to the x. Well, there's nothing tricky about this limit. You just use the continuity of e to the x, and that's the solution to that problem. Okay? So, e to the x goes to 1 as x goes to 0. So how about this limit? E to the x minus 1 over x. How about that limit? Well, let's plug in x equals 0. The top looks like 1 minus 1, and the bottom looks like 0. Guess what? We're in an indeterminate form, 0 over 0. So we have to do some work. Now, if this was a polynomial, I'd try to factor it, but it's not a polynomial. So I have to do something clever. Here is what I'm going to do that's clever. First of all, I'm going to change x to h, and instead consider this limit. After all, x is a dummy variable. Well, this is still not very clever. I'll have to admit, that's not very clever. Just changing x to h doesn't really help much. But it does actually help a little bit. I want you to consider this limit. E to the x plus h minus e to the x over h. I'm just throwing out more limits here. They're getting worse and worse, right? And yet, that's not so bad. What does it look like? It looks like a derivative. In fact, it looks like this. Limit as h goes to 0, f of x plus h minus f of x over h, provided that f of x is e to the x. You agree with this? If f of x equals e to the x, then this is f of h plus, x plus h, and this is f of x. Yes, a question? You know, I just pulled it out of the air. I've seen it before. But bear with me. Bear with me. In fact, this is a derivative in disguise, and there's a section that I didn't get time to cover in chapter 6 of the book. I don't remember exactly which section, but if you look in the contents, you'll see limits which are derivatives in disguise. And it tells you how you might have seen this sort of thing before. And it's not easy. It's definitely not easy. Okay? But just bear with me for a few seconds, and we will see what we get. This is the derivative of f, and actually the derivative of f we already know is e to the x. Because the derivative of e to the x is e to the x. So we've actually proved this general limit here. We've proved that the limit as h goes to 0 of e to the x plus h minus e to the x over h is e to the x for any number x. For any x. That's just the derivative written in a sneaky way. Now, put x equals 0, and you get that the limit as h goes to 0 of e to the h minus e to the 0 over h is e to the 0. So, of course, e to the 0 is 1, so this has shown that the limit as h goes to 0 of e to the h minus 1 over h is actually equal to 1. That's the limit that we want. So you see, this is another way of saying that f prime of 0 is 1 if f of x is e to the x. If you actually use the definition of the derivative and interpret this statement, which is true, which you can prove is true by taking f prime of x is e to the x. So f prime of 0 is e to the 0. So if you actually interpret this statement, you get this limit. But the good thing is that you can just learn it. And I'll change it back to x. This is not the same x as I had before. That's a useful limit to know. Useful limit to know. And of course, it lends itself to other questions like this. And this would be very tricky for a Math 103 exam, but it's not beyond the pale to get such a thing. I don't know, e to the h squared minus 1 over h squared. I just took this and replaced x by h squared. Because they match, you get 1. And of course, you can make it 3h squared or 5h squared, and then you have to multiply and divide. The possibilities are endless. Luckily, this doesn't seem to be in vogue to be asked. But who knows? If you're from a different university, maybe it's fair game. There are plenty of examples in the book. But because I don't think it comes up that often in Math 103, I'm not going to spend much more time on that. I just look at a couple more limits, and then I do have to move on to logarithmic differentiation, which is sort of important. All right. Okay, so let's see, what's the next type of limit I want? Well, suppose instead, and this is in 9.4.3, suppose I play the same game. I'll let f of x be natural log of x. We know that the derivative is 1 over x, right? But of course the derivative is the limit as h goes to 0 of log x plus h minus log x over h, and that equals 1 over x, because we know the derivative is 1 over x. So if you just look at this, we have a sort of formula here, which is the analog of the formula involving e to the x plus h that we just did on the previous board. In particular, if x equals 0, if x equals 1 rather, then you see that the limit as h goes to 0 of log 1 plus h minus log of 1 over h is 1 over 1. And since log 1 is 0, we've proved this limit, which I have seen on occasion, but pretty rare again in Math 103. And you can replace h by x if you want to. And again, it's conceivable you could have log of 1 plus 7h over h, in which case you have to replace this by a 7 and multiply and divide by 7, and you get the answer 7. And again, there are more examples in the book, in 9.4.3. So the status in Math 103 is a little nebulous. They don't come up often. But I've looked back at the last 15 years of these exams, and I'm sure it's come up at least once. Of course, the more relevant ones are the more recent ones. So I'd better just say something about a really important property which I have seen come up. It's like this. We saw the graph of e to the x. You ought to know it. It looks like this. It has the horizontal asymptote there. It goes through the point 1, or 0, 1. Okay, that's y equals e to the x. How does it look over here? What happens? It is true that the limit as x goes to infinity of e to the x is infinity. Sure, it goes up. But how fast do you think it goes up? Pretty fast. What if you compare it to, say, x squared? I don't know, it looks like x squared is going to pass it. Maybe it does. Well, guess what? E to the x passes it back, and it leaves it for dead. It leaves it in the dust. I cannot emphasize how much e to the x just stomps over x squared, or any other power of x. It just dominates it. So, in fact, we can say more than this. We can say that the limit as x goes to infinity of x to the n over e to the x equals 0 for any power n. So if you think about it, x to the n is getting pretty humongous, right? Imagine n is, say, 7. So we're taking the 7th power. So x is like a billion. You take a billion to the 7th power. That's 1 with, I don't know, 63 zeros or something. Humongous number. Yet e to the billion is so much bigger that the ratio of this humongous number over this other huge number is still tiny. That means that the denominator is frickin' huge. Okay, I cannot say it anymore without swearing my head off. Okay? Seriously, that is how strong I feel about exponentials beating up polynomials. Yeah, they kick their ass. There you go. That's as much as I'm going to say. Okay. Anyway, I just want to put that out there. I can't even prove that for you, really, until we do L'Hopital's rule. On the other hand, what's true for exponentials is sort of opposite for logarithms. See, the logarithm is supposed to have a vertical asymptote here. It has an x-intercept of 1. Of course, it's the mirror image of the exponential graph. And the thing you have to understand is it does go to infinity, but it really limps its way there. It's so slow. It's a snail. It gets up there, but it really gets trampled over by any power of x. Even if you take x to the 1/3, which looks like this, x to the 1/3 is pretty slow. It's not much slower than log. At least there's no power slower than log. So if you do this, that also is 0. Log x is smaller than any power for any power greater than 0. When alpha equals 0, it's just a constant. And of course, log x is bigger than the constant. But even if you took x to the 0.0001, which goes like this, takes forever to even get above the blackboard line, but it does. Well, log x is slower than that. It might pass it, but then it will be passed by that power x to the 0.0001, and it will be left for dust. Log x is very, very, very slow. One way to see this, by the way, suppose I take log base 10 of 1,000,000. Who knows what that is?
6.
It's 6, right? Because this is 10 to the 6. Okay? So if I graph 1,000,000, 1,000,000's a long way out. Log is still only up to 6. That's how slow it is. If you want to find when log goes to 7, you have to go 10 times as far. Okay, that's on base 10. Of course, base E, it's a little bit bigger, but not much. Not much. Log of e to the 6 is 6. Log of e to the 7 is 7. E to the 7 is still twice as far. So log is a pretty slow function. Okay, anyway, those are two limits that are going to be extremely useful in Math 104. They may pop up in 103, but again, who knows? So, the last thing I've got to do is talk about logarithmic differentiation. And that will finish what I want to say about logs and exponentials. So, this stuff, again, is this in the midterm? I apologize for not knowing. I assumed that it was, since it was in last week's syllabus, but maybe I'm wrong. Anyway, if I am wrong, then so be it. You're going to have to know it for the final and for the next quiz. So here it is. I will review it again if you do need to know it for the next quiz. Okay. Suppose that y is x to the power sine x. And I want to find dy dx. So this is in section 9.5 of the book. Y is x to the power sine x. How do I find dy dx? I've got a problem. The reason I got a problem is it's x to the something, but that something is not constant. It's not x cubed or x to the 7th or x to the half. Nor is it e to the sine x. If it was e to the sine x, I could just use the chain rule. So, I have to do something clever. And that something is logarithmic differentiation. There's two ways of doing it. I'm just going to show you one method which I think I like better. It's much of a muchness. But this is how I like to do it. If this is what y is, I take log of both sides. And you get log of y is log of x to the power sine x. But of course, log of x to the y, the exponent comes out the front. So this is just sine x times log of x. Well, that I can differentiate. Now what I'd like to do is take d dx of both sides. There's really three sides, so let me write it out again. Log y equals sine x times log x. Okay, how do I differentiate log y? I've got to use implicit differentiation. Because if it was log x, what would the derivative be? 1 over x. So if it's log y, the derivative is 1 over y dy dx. Right? If this was sine y, the derivative would be cosine y dy dx. With log y, it's 1 over y dy dx. So that's just implicit differentiation. Then I just have to differentiate this, and I'll use the product rule. And just quickly, it's v times the derivative cosine x plus u times the derivative of log x which is 1 over x. So I use the product rule on the right. Well, I don't want 1 over y dy dx, I want dy dx. So dy dx is y times this mass. And of course, I got to get rid of the y. Y was just x to the sine x. So I just replace that. And that is the derivative of x to the sine x. You wouldn't have guessed it. It's not the most obvious thing. Okay, so I want to review the steps that I did over here. And this is what's true in general. If y is f of x to the power g of x, where both the base and the exponent involve x, then the method is, step 1, take log of y, which has the benefit of dropping the g of x out the front. You'll get, in general, you'll get g log f. These could be any functions of x here. Then you do d dx of both sides. And you always get 1 over y dy dx. That's because you always have log y on the left. So you should be used to writing 1 over y dy dx. And then you just have to differentiate this, normally using product rule or whatever. The point is that it's just a product. You might need the chain rule as well, but it's nothing like this. It doesn't have f to the power g. It's just a simple sort of thing involving products and compositions. Then finally, once you've done this, you have multiply through by y, and you get dy dx equals y times mess, which comes from this, and then replace y by the original function f of x to the g of x. And that is the template for logarithmic differentiations. And I followed that exact template there. Okay? Let me show you another example. And this one, suppose y equals x to the a. Well, this, you know what the derivative is, but we never actually proved it. I just sort of stated it. We never actually proved this, that the derivative is ax to the a minus 1. Well, now that I have this logarithmic differentiation, I intend to prove this. Let's just take log of both sides. So you get log of x to the a is just a log x. So if you take d dx of both sides, that's the next step, you get 1 over y, dy dx, is equal to, and I need to differentiate this. This is just a times 1 over x, because the derivative of log x is 1 over x. So this means that dy dx is a times y over x. But what is y? Y is x to the a. Of course, x to the a divided by x is x to the a minus 1. And there's the proof that the derivative of x to the a is ax to the a minus 1 for any number a. Kind of nice, huh? So the reason that the power gets knocked down by 1 is actually because the derivative of log x is 1 over x. And when you multiply by 1 over x, the power goes down by 1. That's sort of where it comes from, in some weird, whacked-out sense. Okay? So, actually, you can solve any problem. If you want to practice this and you cannot find any examples, take any two functions that you know how to differentiate. Let's take some functions. What's a function you know how to differentiate? Come on, say something. 2x squared? So suppose you take y equals 2x squared to the power of, what's another function we know how to differentiate? Maybe a trig or something. Cosine x. You can differentiate that using this method. Huh? You want to make it more complicated? Okay. That's probably good enough. Right? You can differentiate that using the above method. So what you do, take log, use the product rule, and follow that method. Not so bad, huh? Let me show you one more example. I'm not going to do that one. I'll leave that as an exercise. Let me show you one more example that doesn't look like it even needs log differentiation. And in some sense it doesn't, but you'd be insane if you didn't use it. It's going to take me a while to even write up the question. But here goes. Suppose y happens to equal this monstrosity. X squared minus 3 to the power of 100 times 3 to the secant x over 2x to the 5 quantity log x base 7 plus cotangent x all to the power 9. And you guessed it, I want to know what's dy dx. Okay, so I could leave you and come back in 2 hours and you might have finished it if you just do it the regular way, right? You're going to have to use a quotient rule. This needs a chain rule. This needs a chain rule. This needs a chain rule. This needs a product rule. Excuse me. So, this is not the way to do it. Instead, let's take logs of both sides. What do we get? Well, no, I'm not differentiating yet. I've got to take the logs. I get log y here. I will differentiate it soon, but I get log y. I need to take log of all this. Well, here's the beauty of it. This is just a quotient of two things. In fact, it's a product. This times this, divided by this, divided, and that. So I could write log of all this, and probably I should, but I don't want to write this out again. So instead, I want you to understand why it's this. Log of the first term plus log of the second term minus log of the first factor on the bottom minus log of the second factor on the bottom minus log of the last factor of the bottom. Okay, it's a bit of a long expression there. Do you all agree? I've just used the log rule. Log of a product is the sum of the logs, and log of a quotient is the difference. So everything that was on the top, every factor got its own log. Every factor on the bottom got its own log with a minus out the front. Okay? You need to be able to do these manipulations with log rules. Basically, all I've done is log AB over CDE is log A plus log B minus log C minus log D minus log E. I've squashed that up there because it's not a very useful formula to know, but that's basically what I've done. All right? But we can do even more. This is the 100th power. That comes out the front of the log. So it's 100 log x squared minus 3 plus secant x log 3 minus log 2 minus 5 log x minus 9 log of log 7 base x plus cotangent x. So all those exponents have just dropped right out. And somehow everything is much simpler. although it is logarithmic. Now, let's hit both sides by d dx, and again, now we get what you wanted, 1 over y dy dx, and I just have to do some derivatives. So still got a chain rule to do here, log of x squared minus 3. Actually, the chain rule with logs is not that bad. What's the derivative of log x? Okay, so what's the derivative of log of a watermelon? Times the derivative of the watermelon. It's 1 over the watermelon times the derivative. In fact, what's the derivative of log of y? It's 1 over y times dy dx. And that's exactly what we did over here. So following the same template, it's 1 over x squared minus 3 times the derivative of x squared minus 3. So derivative of log anything is really easy. Oh, my microphone is gone. Check. Am I back? Yes. I'm back. Did we miss much? Okay, not much. Just about watermelons. They're very tasty. Don't choke on the seeds. Okay, so we have 100 log x squared minus 3. The derivative is 1 over that quantity times the derivative of that quantity. What about this? Do you have to use the product rule here? Who thinks you have to use the product rule? No one. No one's going to use the product rule there. No, you shouldn't use the product rule. Okay. Talk about leading. Look, this is just a constant. If it was 5 secant x, you wouldn't use the product rule. You just say 5 times the derivative of secant. Well, 5 is as much a constant as log 3. So this is log 3 times the derivative of secant x, which is, do you know it? Secant x tan x. Okay, you certainly need to know that for tomorrow night. How about the derivative of log 2? What's that? 0, it's a constant. Derivative of log x, 1 over x. And for this last term here, I'm going to do the same thing. It's log of something. The derivative is 1 over that quantity, which is log x base 7 plus cotangent x. And now I just need to multiply by the derivative of that quantity. The derivative of log x base 7 is 1 over x natural log of 7. That's what we did earlier. And the derivative of cotangent is negative cosecant squared. All the cos have negatives. Whew. Finally, we have to multiply by y. And y is all this original stuff. So dy dx is the original y. That's y, and I better write it out. Oh, x squared minus 3 to the power 100. 3 to the secant x over 2x to the 5 log x base 7 plus cotangent x all to the power of 9. Whew, times all this, which I can simplify a little bit. I'll write this as 200x over x squared minus 3 plus log 3 secant x tan x minus 5 over x minus 9 over... Oh, here it is again. I'm sick of writing log x base 7, but I have to, or else you won't respect me. Oh, there we go. Well, there should be a square bracket here, I guess. Ta-da! I'm not. Okay, how much did you miss that time? Am I still here? Did you miss much? Okay, I wasn't even talking about fruit this time. Okay, so logarithmic differentiation, you can use it for f to the g, where they both involve x, or you can use it for a nasty expression involving a product or a quotient or something like that. Okay? Any questions about exponentials or logs? Okay, let me just say that in the book, and this is more for the benefit of the video, but you might as well listen to it anyway, 9.6 is on exponential growth and decay. Used to be in Math 103. It isn't anymore. It's in the book. Okay? Those in the room, you don't need it. Okay? Who knows? Maybe you need it. I'm not going to talk about it. Sorry. Am I out again? No. Good. 9.7 is about hyperbolic functions. It was never in Math 103. Or at least it hasn't been for 20 years. So you don't need to know it. Again, it's in the book, just in case. Good. Okay. So, something miraculous has happened, and I'm only running 5 minutes late, which is good. But it means I don't have much time to pause. What I want to do is spend 40 minutes going over everything we've done so far. Not necessarily in the order that we did it. And again, I'm presuming that the stuff I talked about tonight is actually in the midterm. If it isn't, I'm sorry, we'll try to resolve this after 9:30. Basically, you need to know something about limits. Now, we did limits at the beginning, in the middle, just now. Let me just sort of try to consolidate everything that we need to know about limits. And you might want to look ahead to section 14.2. If you look at 14, it's gone out, hasn't it? If you look in section 14.2, you'll find an overview of limits. And the only thing that you don't need to know that's in there is actually L'Hopital's rule. You do not need to know L'Hopital's rule. But if you look at 14.2, I think you'll find it quite useful for this midterm. Okay, so let me just run over the main points from this section. If you have a limit, first try substituting. So, limit as x goes to something, try plugging in that value of x and see if it works. Try substituting. Now, if you get a nice number when you substitute, that's probably the answer to the limit. There's nothing else you need to do. But maybe you don't get something nice. Maybe you get something like b over infinity. If b is some nice finite number. I'm still on? No, I'm off. Take a second. Okay. Am I still visually there? You didn't turn off the video? They shouldn't let me on TV. Tell you. Bad plan. Sorry about that. So those are my thoughts on the meaning of life. Did you get that? Oh, never mind. You just walked in. You must have no clue what's going on. Well, that's okay. None of us here do. Okay, we have a new battery on the microphone, and I think everything should be fine. So, here goes. Limits. First of all, try substituting. If you get something nice, cool. If not, maybe you get something that looks like b over infinity, or b over minus infinity. In that case, the limit is 0. So the sort of classic example is just something simple like limit as x goes to infinity of 3 over x to the 7. You plug in infinity, you get 3 over infinity, because infinity to the 7 is infinity. Of course, it's not actually infinity. It's 3 over a really large number that's getting larger and larger. Of course, that limit is 0. It's also possible that you get b over 0. In that case, you're dealing with a vertical asymptote, most likely. Unless, of course, b is actually 0 as well, but let's talk about that later. This is where b not equal to 0. So you just get some finite number over 0. It's probably a vertical asymptote, and it's up to you to work out which sort it is, whether it looks like this, or like this, or like this, etc. So there are 4 different types, and the only way you're going to know which one it is to plug in some values. Investigate the sign SIGN, when you are close to this asymptote here. If it's positive to the right and positive to the left, it looks like this. And so the two-sided limit would be infinity. Again, this is a review of a review. So I've already talked about this exact point. I don't want to go over it again. I just want you to understand that you have to review this particular aspect of things. Make sure you know how to deal with this. Okay, so what if it is a 0 over 0 case? Well, that's an indeterminate form. Now, it's possible that it could be something like the limit as h goes to 0, e to the h minus 1 over h, which I talked about earlier, which was a derivative in disguise. Again, I didn't have time to cover that section, part of chapter 6, on limits which are derivatives in disguise. They're pretty nasty. I haven't seen too many of them in at least Math 103. But that you're going to have to recognize as a derivative. That's the way to do these. They're pretty mean. They don't come up all that often. So that's a sort of general rule of thumb for dealing with 0 over zeros. Sometimes they're derivatives in disguise, but most of the time what you're going to have to do is use various properties of the different functions that we've looked at. Polynomials, trig functions, that sort of stuff. So let's just spend a few moments looking at some of these principles here. And you need to make sure that you're aware of them all. Actually, before I go into the functions, I've got two more points. If you have square roots and they look like you can't resolve them by other means, remember the conjugate trick. Multiply and divide by the conjugate. So an example of where that comes up is if you had to work out something like the limit as h goes to 0 of 4 plus h minus 2 over h. The conjugate trick says multiply top and bottom by the conjugate expression. And once you start there, you can hardly go wrong as long as you use the difference of squares on the top. And again, I've done examples of this, quite a few, so I'm not going to dwell on that. This is just a potted summary. So when I see this limit, this is what you have to do here. You have to multiply and divide by the conjugate. Okay? Again, one other thing, if you see absolute values in a limit, the tendency is to panic. But what you have to do is convert the function, convert everything to a piecewise defined function. And just to remind you, here is a definition that you should know because it's really bloody useful. The absolute value of x is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. Please remember this. Be able to write it without even thinking about it. Because if you can write that, then you can deal with the absolute value of anything. For example, the absolute value of cosine x, if you should happen to have a limit involving this, you can convert this into a piecewise function. Of course, it might be absolute value of cosine x over 1 minus x or something like that. But if this is a piece, all I'm going to do is change x in 5 places. There's 5 places where x come. Count them. 1, 2, 3, 4, 5. I'm going to change them in all 5 places. This is cosine x if cosine x happens to be greater than 0. And it is minus cosine x if cosine x happens to be less than 0. Again, that's not solving a limit problem, but I'm just trying to say that if you had a limit, then you would change this into this, and then you would be able to investigate two-sided limit by looking at a right-handed limit and a left-handed limit, and look at which one of these applies and replace cosine x appropriately. Again, no examples because I've done it before. I've done problems like this before, and you can find some in the book. And we can look at examples after 9:30. As part of the summary. I just want to remind you that is how you deal with absolute values in a limit. Okay, for those of you who are just coming in, I know I said I would start the summary at 9. Unfortunately, in some sense, I finished a bit early, so I've started the summary a little bit early, but it's all on the board so far. It just starts down here where it says limits, and then it continues. So I apologize for changing my schedule slightly on the fly. Right, so what else am I talking about here? Okay, now I've got to tell you about different types of functions that we've looked at and the limits that come up. The first type is polynomials. And poly-like functions. Okay? If you get a 0 over 0, then you probably need to factor where possible. And cancel. So I'm sort of thinking of this sort of limit here. You have to factor the top and then cancel. We looked at that limit, in fact. Now, don't forget the difference of cubes. This is a useful formula. You may need this formula in order to factor. And you might as well learn the sum of cubes as well. Okay, that's just basic algebra, but no one is going to hold your hand and tell you, oh, by the way, to factor x cubed minus 8, you write x minus 2, etc. You have to know this formula and apply it. Okay? On the other hand, what if it's more of the infinity over infinity case? That's large values. Well, there you don't need to factor. In fact, you don't want to factor. In this sort of example, limit as x goes to infinity, you don't want to factor the top, really, even if you can, which you can. You could factor the bottom, too, if you really want to. It's a difference of squares. Pretty messy difference, but why not? On the other hand, you don't need to. The largest term dominates. The top behaves like x squared. So multiply and divide. In fact, let's say divide and multiply. Each poly term by leading term, by its leading term. Okay, so in this particular case, the top behaves like x squared because that's the largest term. So I take x squared minus 3x plus 2. I divide and multiply by x squared. And I do the same on the bottom. 5x squared minus 8 behaves like its leading term, 5x squared. So I divide and multiply by 5x squared, etc. The beauty of this is that these cancel out and you just get 1/5, and then you've got to show that each of these goes to 1, which is not very difficult. Again, I've done plenty examples like this in previous weeks. Okay, so polys, completely different if you get the 0 over 0 from the infinity over infinity. Just different techniques. Factor or multiply and divide by the leading term. With trig, which is my next one, again, there's a difference between small values and large values. Oh, lots of chalk. Okay. trig. What do I want to do first? Okay, by the way, know the graphs. Got to know the graphs. They're in chapter 2. Know the graphs of all 6 trig functions. Now, if you're in the 0 over 0 case, you probably need to use the fact that the limit of sine A over A as A goes to 0 is 1. But don't forget, it's not just sine of x over x. It could be sine of any small over the same small. So don't forget to multiply and divide by that same quantity. E.g., if you have the limit as x goes to 0 of something like this, sine of x squared over 3 sine x. 3x sine x, that's what I mean to say. Sine of x squared over 3x sine x. The way I deal with this is, I say, I would like to multiply and divide by this quantity. I want sine x squared over x squared, and I will multiply that by x squared. Let's keep the 3. Let's keep the x. And sine x, I gave the same treatment. I'm going to make this sine x over x, but I multiply by x again. So it seems like I've made the situation more complicated. I've made the numerator more complicated, and I certainly made the denominator more complicated as well. But the beauty of the whole thing is that this matches this, so this limit is 1. And this matches this, so this limit is 1. I can also cancel out that x, and that x squared. So I just get sine x squared over x squared goes to 1. This is 3, and that goes to 1, and the limit is a third. To me, that is the easiest way to do it, even if it looks ugly. But that's the idea. In a similar vein, the limit of tan A over A is 1, and that's because tan is sine over cosine, and cosine of 0 is 1. This is not true for cosine. It only works for sine and tan, okay? Not cosine. Right? Now, what about when you have large values? This is for small values. You're taking sine of a small number. So it's 0 over 0 is the normal case. What if it's large values? What if you have to take sine of infinity, if you like? Well, you can't take sine of infinity. In fact, you can't take sine of a large number and have it go to anything. It oscillates back between minus 1 and 1. So the best you can say is that minus 1 is less than sine of anything is less than or equal to 1, and this would lead to a squeeze or sandwich principle type argument. So if you're dealing with sine of x squared, see in this problem, x goes to 0, so I'm taking sine of 0, sine of 0. It's all sine of small. But in a problem like limit as x goes to infinity of sine x squared over x, well, there I'm taking sine of a large number, and I cannot use sine A over A. I have to use this and the sandwich principle. This is also true for cosine, by the way. But not tan. It's only true for sine and cosine. So at infinity, or for large values, squeeze principle, this functions with sine and cosine, but not tan. But for small values, those nice relationships, the ratio relationships, work for sine and tan, but not cosine. Sine is the only one that it works for both. So I kind of like sine. All right, that's all I have to say about trig. I'm going to skip exponentials and logs, so that would be x and log, simply because I already talked about them for an hour and a half. But all the limits that I wrote up there really belong in this summary. Again, for those of you who came in a little later, 14.2. Look at chapter 14.2. It's further on in the book. You might think it's past the midterm, and it sort of is, because it mentions L'Hopital's rule, but everything but L'Hopital's rule we've already done. So look at section 14.2. It's just this summary spelled out with references in the earlier chapters where to look for the complete explanations. Okay, so that's what I want to say about limits. There will almost certainly be a problem that says, find the following limits. This only applies to Princeton, but I suspect most schools would do something similar. Limit, 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 limit. One might be trig, one might be exponentials, one might be polynomials, who knows? Okay? But even though you did them in a different order, you now have to study them in the order that I've just given you. Well, that's my advice anyway. Know how to do a whole grab bag of limits. And I expect at 9:30 after we finish the summary, you will have limits to ask me. Probably. So we'll see how we go. Now, another huge topic is derivatives. Okay? You've got to make sure that you know the derivatives of powers of x, and don't forget the two most common ones that you should learn. I recommend that you learn root x directly and 1 over x comes up so often. If you learn those two, you save yourself a little bit of time that you could use for something more useful. See, I know you could convert this to x to the 1/2, and you could convert this to x to the -1, and then you get it minus x to the -2, and then you have to convert it back to this. If you just learn these two, because they come up so often, instead of having to use this, I think you'll save a little bit of valuable time. Okay, you need to know the derivatives of the trig functions. Sine, cosine, tan. Okay, they're all in the book. I'm not going to write them up. Make sure you know the 6 trig functions. Don't forget secant, cosecant, and cotangent. Okay? You also have to know the derivative of exponentials, which I wrote up earlier today, and logs. And don't forget b to the x as well as e to the x, and don't forget log x base b. No question, just a stretch? Okay. So make sure you know those derivatives. Also, make sure you know how to use the product rule, the chain rule, and the quotient rule. Product, quotient, chain rules with them. Okay? So these are things that you need to commit to memory, at least these ones, and then practice using these rules. You've already done some practice, but... Also on the line of derivatives, make sure you know how to differentiate implicitly. That's just the chain rule, but it's a little tricky. The particular implicit differentiation question that comes up all the time is find the tangent equation, or the equation of the tangent line, at some point for, and then insert implicit relation in here, implicit stuff. And when I say implicit stuff, remember, I mean not y equals something, but just some more complicated equation involving x and y's. The way you solve this is you whack both sides with a d dx, and you will find dy dx as a result if you do this properly. And you plug in these points. Plug in that, and you will get the slope. And then, and this is where a lot of people get stuck, you found dy dx, you just have to finish the problem. You need to find the equation using the point slope form. Because you know the slope and you know a point that it's gone through. So there's the rough outline of how to deal with implicit differentiation problems. Of course, they're not all like that, but that's a very common question. Again, I've done examples in the past. I just want to remind you that that's something you need to look over. There's a couple of other types of differentiation you have to know. You're supposed to know the definition and how to apply it in some basic cases. So don't forget, you have to, well, let me write it up. Still, while we're talking differentiation, you have to know the definition. You've seen this before. Just be aware that if the problem says find the derivative of blah something, some function, using the definition of the derivative, you have to do it using that formula and replacing f and actually computing the limit. Okay? I've seen these questions come up before. And finally, you need to know log differentiation. Again, it's not clear to me whether that's actually in the midterm. If it is, then you need to know it, but I just talked about it not even half an hour ago, so I don't have anything else to say about it. Great. So that's what you need to know about derivatives. So 2 big topics, limits and derivatives. What else is there? You need to know about continuity. Okay, that's in chapter 5 of the book. I should have said all the derivative stuff is in chapter 6 of the book. You need to know something about continuity. So what do you need to know? You need to know the definition, which is that the limit as x goes to a of f of x equals f of a, and that both sides exist, in fact. So this is continuity at a. So you should know that definition, and you might have to apply it. You should know some simple examples. You need to know the intermediate value theorem and be able to apply it. Again, don't have really enough time to actually state it, but I have stated it before. And you can find it in chapter 5. You also need to know the max-min theorem. Now that max-min theorem is a bit of a weird one because there's not a lot of questions that you can ask directly based on it. But I have seen in certain previous Math 103 exams complete the statement of the max-min theorem. If x is a blank function, continuous, you have to fill in the word continuous, on the interval blah, then etc. So look up the statement and make sure that you can actually quote the statement of the theorem and have some clue about what it means. I do have one thing I forgot to say about the intermediate value theorem. Trick. There's one little trick. Sometimes you have to put everything on the left-hand side. And I want to remind you of an example. Here's the classic example. If you want to show that x equals cosine x has a solution, you need a function, e.g., show that this has a solution. We did this example, so I don't want to spend much time on it, but the first step was to realize that if that has a solution, then so does this, and vice versa. That's what you really need to solve. So convert a problem into this, and let f of x equal x minus cosine x, and then try to find a value where f of x is positive and a value where f of x is negative. And then invoke the intermediate value theorem. Okay, and you also need to know, as I say, the max-min theorem. There's a particular type of problem involving piecewise defined functions. Unfortunately, I did not get much time to talk about this. In fact, I didn't really get any time to talk about it, at least on the videos. So let me talk about piecewise defined functions for a few minutes. We're getting quite close to the end of the summary, which is good. It means that everything you need to know is already being talked about almost. Okay, if you want a piecewise function to be differentiable, suppose you have a function that is defined piecewise and you want it to be differentiable, or you want to see if it's differentiable. The only interesting point is at the join point, which is where you switch from one piece to the other. So the example that I'm going to work with here is, and this is similar to one that is in section 6.6 of my book, so please review that section if you want to know more about these, let g of x be equal to minus x squared plus 4 if x is greater than or less than or equal to 1, and minus 2x plus 5 if x is greater than 1. Okay, so the question is, where is g continuous and where is g differentiable? And I'm actually going to work this example in the midst of the summary here. Where is g differentiable and where is g continuous? Or maybe I'll do continuous first. Okay, clearly g is differentiable everywhere except maybe for 1, the point 1 itself. Right? In fact, it's tempting to say g prime of x is equal to minus 2x and minus 2, which it is if x is less than 1, and it's certainly minus 2 if x is greater than 1. The problem is what happens at x equals 1. So g is automatically differentiable and continuous everywhere except maybe at 1. So that's the only point we have to check. So basically, you need to check continuity at x equals 1. Suppose I just want to see if g is continuous at 1. Don't even worry about the derivative. What do I have to do? I have to look at the left-hand limit and the right-hand limit, and they have to match. So what I want to do is match limits. So let's look at the left-hand limit. As x goes to 1 from below of g of x, what is this left-hand limit? Well, when x is below 1, g is minus x squared plus 4. And if I actually work out this limit, all I have to do is plug 1 in, and I will get minus 1 squared plus 4, which is 3. Whereas the right-hand limit, well, when you're to the right of 1, g is negative 2x plus 5. And if I plug in 1, I again get 3. And these are the same, so the curves match as you go from the right and the left. Continuity. So g is continuous at x equals 1. If these were different numbers, it would not be continuous. And of course, g of 1 itself is actually equal to 3 from this one, but it wouldn't matter if I used this one. Okay? Now, that does the continuity. What if I want differentiability? For differentiability, I need two things. I need continuity, so you have to do all of this. See, it's not, if the curves don't even match, if the thing is not even continuous, it can't be differentiable. So if you want the thing to be differentiable at 1, it's got to be continuous. You have to do this first. And you need to check the derivatives. Repeat for g prime. So I'm going to take these limits, but instead I'm going to use the derivatives. So limit as x goes to 1 from below of the derivative of g. And I'm just repeating the exact computation, but instead of using g, I'm going to use g prime. I'm going to use this derivatives here. So from the left, it's minus 2x, and if I plug in 1, I get minus 2. From the right, well, the derivative to the right is actually minus 2, as we can see from up here. So the right-hand derivative has limit negative 2, and these also match. So g is differentiable at x equals 1. I want to emphasize, this shows that g is continuous. This and this are necessary to show that g is differentiable. You need to do both. Differentiability is more than just continuity. Okay, as I'm erasing this board, you have a chance to shout out a question, if anyone has one, about that example.
I need to do both.
for differentiability? Well, it's possible. Here's a little sketch. Suppose I organize so that the slope here is 1, and then I have the function jump down to a line of slope 1. If you just match the derivatives, you'll find they match at the join point. There it's 1, and there it's 1. But the function is not even continuous, so it cannot be differentiable. Okay, so that's the thing you're trying to avoid. So it needs to be actually like this. The only other comment that I have, by the way, about this example is if you're dealing with absolute values, I said convert those into piecewise functions, right? I said that earlier. This is the technique that you can use then on those piecewise defined functions to see if certain limits or derivatives exist. So that's very useful. Did that answer the question okay? Is that it?
What if it's continuous, it's still not differentiable?
That's correct. It can be continuous and not differentiable like the absolute value of x, but it cannot be differentiable and not continuous. If you're differentiable, you have to be continuous. But you can be continuous and not differentiable. Okay, I'm almost at the end of the summary because I'm almost out of time. Or vice versa. In fact, I have 4 minutes, but that should suffice. You ought to know something about motion. And the formulas that are particularly useful involve motion with gravity. So we're talking constant acceleration. So if you're dealing with gravity minus g, because it points downwards, you might as well know the formulas we looked at last time. X is minus a half gt squared plus ut plus h. The velocity v is the derivative of this, which is minus gt plus u. And the acceleration is the derivative of this. And I ought to say what these things are. This is assuming that h is the initial height. And u is the initial speed or velocity. And don't forget that if you throw it upwards, that's positive. Down is negative. This doesn't cover every example, but basically the only other thing I can tell you about velocities in general is that you ought to know that if x is the position, in general, if x is the position at time t, then the velocity v is dx dt, and the acceleration is dv dt. So those two formulas are true in general, not just in that particular case. And so if it's not just straightforward dropping a ball or throwing up a ball or something like that, then, but a more complicated motion, you need to know the velocity is dx dt, or else you're screwed. Quick question. They'll tell you what g is. Sometimes 9.8 or 10, or maybe it's in 32 feet per second squared. A g is positive, yeah. I see the acceleration is minus g. If upwards is positive, then the acceleration is downwards, so it's negative. Okay? Then the only other topic, really, is related rates. You need to know how to solve those word problems. I did this last time. Suffice it to say that the most valuable piece of advice I can give you about these problems is that a rate of change of some quantity q, if you see the word rate of blah, where blah is a quantity that you have called, say, q, this is dq dt. It's the derivative with respect of time. That is what the definition of rate is. It is a time derivative. So I will use my last 2 minutes to quickly give the brief overview of how to solve related rates problems. It was a 4-step procedure. I'm going to have to take that in a few seconds. The 4-step procedure looks like this. Read the question. Pick variables. And note which one you want to take the rate of. You need the rate of. Okay, so in some sense, step 1 is translate from English words into math symbols. You have to say, let V be the volume. Let r be the radius. And I want the rate of change of the radius, so that's the one I'm going to take a note of. Step 2. And this is a little different because I got stuck at the end here. You want to write down equations, and there might only be one, or there might be several equations relating the quantities. So if you know V is the volume and R is the radius, and you know it's a sphere, then you write down V equals 4/3 pi r cubed. That sort of thing. You want to try to relate the thing. If you have more than one equation, try to solve simultaneously to reduce the number of equations, if possible. That's something I didn't put on the step last week, and I would have saved a lot of time if I did. In fact, it's not even in the book, but maybe by the time you read this, I will have edited it so that I added in that little section, because I certainly got tripped up by doing something the hard way. Only 2 more steps, and then I'll be done with the summary. 3, differentiate implicitly each remaining equation. And step 4 is finally substitute values. So again, if it says, what is the rate of change when the radius is 6? You do not substitute first before differentiating. You must do the substitution after the differentiation. Solve for dq dt, where this is the one that you want, and then write a sentence, translate back into English, describing your rate. So the rate, I found the rate of change of volume is blah. Okay, so here we are. We have run out of time for the video. There is a summary. Next time we continue with inverse functions.